exam tomorrow on electrodynamics, and there's quite a lot to review. Let's get started with vectors and rotations and stuff. So here we have how we have these rotation matrices. You do it around the x, the z, or the y. So you get this plane, right? So there's a plane there, there's kind of a plane here, another one here, and there's always this one. So just kind of have to maybe remember these matrices. And you apply them by just multiplying the vector by r, and then it becomes A prime. And just keeping in mind that R transpose times R equals 1, or the identity matrix, and the determinant of this stuff is 1. So now we can also consider the conjugation identity that's like this. We might have to do 3 rotations. Notice that this is a rotation in X, and then we have YZY. So that's kind of interesting. This is a matrix. So A, I, B, J. This is like 2 different indices. And this is kind of the next section, is we're looking at index notation. So how do we how do we use indices? There's a lot of different ways. If you have the same index across them, so you have A, I, B, I, then that's just the dot product, and it becomes a scalar. You can do this with both 2 vectors or the gradient and a vector. So you get scalars out of that. And notice that, again, we just have matching indices, and that just makes a number. But if you have non-matching indices, then you get a matrix. It does not equal 0. You might think that if it's not matching, then you're kind of multiplying opposite components and they all equal 0, but it's really just building a matrix. And there's a lot more about this index notation, so I guess we'll kind of take a quick peek. So this is like the delta function, ij, dij. It's just a 1, 1, 1, like that, which equals 1. The determinant at least equals 1. This is the identity matrix here. And that's basically what this dij is trying to do. And it's also the same thing as a little metric as well. So this is like a 3D metric. We're to discuss how you can get scalars out of these indices, but notice that there's other ways to use it. So like you can stack on another vector on top of it, and you have to switch indices. So these 2 indices are the same, they're both i's. Looks like a little I right here, I in here. And then this is a j, which is a different index. So these 2 kind of pair together, and this is different. And it makes a scaled vector. So notice that we took a scalar and we multiply it by a vector. So really what you're getting is an f times vector, which I guess you could call it capital F with a single index underneath it. And in fact, using just a single index, you essentially just make a vector. So you just take a letter, give it 1 index, and it gives it 3 dimensions. So that's kind of cool. Here again is the Kronecker delta written in a different way, where it says I equals j. If I equals j, it's 0. That's exactly what the identity matrix is. And if you want to build the Kronecker delta, notice how you have to do this. You kind of have to have, I guess I'll give it green. These guys have to match. And then this thing on the side over here, I guess I'll give it purple, becomes the index to use here. So the matching index kind of goes away, and you're left with a single index. And that's just a vector. So that's pretty important usage. Let's take derivatives now, I guess. And derivatives are important. Like the reason we do these indices is because we like to do derivatives and stuff. So this is fine. We'll take a little derivative of the position vector, and notice that this is very specifically the d over dx in the x direction. D over dx. I don't know, derivative in terms of x instead of in terms of y. And notice here, because of that, we only get the x hat direction. If this was like a dy in for the position vector, you could also think of this as like r, if you want. It's kind of like this. It's just a position vector. Well, we'll give it a general x like this. So the position vector just has x, y, and z in it. So if you take a dx component, you're just getting the x hat. Because what you've done is you've taken a partial of x, partial x, for all three of these, and these things go to 0, and then this is left with just kind of like a 1 here, but it's in the x hat direction. So that becomes the I hat vector. Okay, yes, it's kind of confusing how to do all this derivative stuff, but here's another example. You can take, if it was not just x, notice this specifically x here in the partial. Here, we're taking um, partials of three different x's. And if you're doing like dxj here, you're giving a little index there, which means that it's not specifically the x direction. It means that it's the x, the y, and the z direction, or any. And on top, you just have a regular old uh, xk. And it's literally exactly this, where you're taking a partial in all three directions, and then you have this x. And these are not matching indices. It's very important. If they're not matching, then it becomes a delta function. If they are matching, well, I'm not going to worry too much about that because it's going to be too confusing for now. We want to focus on these things that are true. Remember these things that are true, these little formulas that are true, and then if you spot them anywhere, then you know what it actually is. And of course, there's going to be some things that you might not recognize, and we just kind of have to write down the identity that would help to clarify that particular thing. So if we see this thing somewhere, we don't know what it means, then we should probably write this in a piece of paper so that we can kind of refer to it and recognize that it's just a delta function. And notice that jk or kj doesn't matter, it's the same thing. It's nice. So let's look also at this very interesting thing here, which says that the nabla, the gradient, it doesn't commute. So you can't do like here you just have regular vectors. If you do a dot b, that equals b dot a. It's the same thing when you multiply, 1 times 2 is the same as 2 times 1. Same thing. Doesn't matter if you're doing it in one direction, one dimension, or 3 dimensions, it's always the same. But if you do that with a gradient, these derivatives, they're very delicate, so you can't just move derivatives around willy-nilly. You have to choose where you're going to put the derivative because it operates on the very next thing. So that means that if we do a dot nabla, um, that becomes this, ai di, right? And if you do it with the nabla dot a, then it becomes di ai. So let's look at what that means. Let's go ahead and stick another vector after it. We use b. So you stick another vector after it, and then look at what happens. You have ai, and then you're taking a di of b. So you're taking derivatives of b here. It's kind of like you're taking the gradient of b in this situation. But if you flip it around, then you're no longer taking the gradient of b. Now you're taking the gradient, or really the div of a, and you're multiplying that by b. So this is a very important thing to recognize that you can't flip the nabla with the vector. It's got to be in the right order. Otherwise, the meaning completely changes. Because the operator acts specifically on the very next thing in line. This operates on A. This is waiting to operate on something. You kind of multiplied components of A times that you've scaled it by that, but whatever. Okay, so this is all great and amazing. Let's continue our venture into these delta functions. So you can multiply two of them in two dimensions and you get delta squared, delta to the third, delta to the fourth, depending on how many dimensions you try to jam together. Um, but here, notice that delta squared is actually the same thing as delta r divided by 2 pi r. Hmm, don't really, it's hard to sort of understand what the heck this is even trying to do, but I guess we're putting it in terms of like circles instead of squares. So you have to divide it by 2 pi. And then over here, you have d to the third, you actually get 2 pi r squared on the bottom. D to the fourth gives you 2 pi squared r to the third. Now hopefully this is correct, because I don't even know what the heck this even is doing, but sometimes we have to do deltas in multiple dimensions, not just one. And here's the official meaning of the delta function. There's so many different ways to look at this delta function. It's the identity function. There's like this like input or this on and off type of usage for it, which is the identity, like in a different form. And then, you can pull it out of these derivatives of partials of x position vectors, and you can put them in three dimensions. And then, you also have this integral form here. This integral form says that you just multiply some function by the delta function, and then you pull out the value at zero. What? Okay, so that's insane. And here's another way to think about it. If you integrate this thing from infinity to infinity, it equals 1. And if you integrate it from 0 to r, specifically dr, it also equals 1. This is the same things written in terms of x's, an entire axis, or r in terms of a radius. So yeah, that's the delta function. It's pretty intense. Oh, there's so much about this chapter, this review that we have to cover. It's kind of insane. So here's some more stuff. I guess this is now the Levi-Civita tensor is sort of next. It's kind of the partner to the delta function. So while the delta function does this dot product stuff, um, kind of does this dot product stuff, I guess. I don't know. And then this Levi-Civita stuff is a cross product. So the cross product, how do we write that? Let's go ahead and look at this. This little piece right here, this is the cross product. So we're basically taking A cross B, and we're giving it a notation here. I, that's the I that we can use here. And then we just start pairing these guys. So JK becomes JK. Boom, and you have this cross product sort of embedded in this. That's literally just what it means. Um, it turns out to be a vector. It's vector Fi. So we've just made this into a vector. Should mean that the final. I think there's like a right-hand rule to this, but I think that you can have other components, so don't worry too much about that. Anyway, so then we could do that with a nabla, and again, you just kind of do a delta j here, ak, and then all of a sudden you get this vector out of that with a fi. So this is one way to start using the Levi-Civita, is to just start encoding cross products with it. Here you can multiply two Levi-Civitas together with different indices. One of them is matching. And because of that, the matching thing goes away, and we're left with IL, JM, and it's kind of like we're pairing them. So red, so here's green, and here's L. Red, so green, red, blue, I don't know, this one, green, blue, red. Green, here's blue, and here's red. So red will go away, and you're going to be left with green, 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 and then you have blue, blue, and then they're mixes. So this is like green, green, and then blue, blue. So that's a good way to think of the Levy's zeta there as well. Let's take a look at this other way to think about it. It basically just means that you have a 1, negative 1, or a 0 that you're flipping between. Whereas the Kronecker delta was just 1 and 0. Here you tossed in a negative 1 as well. And so that's just basically like this. Um, think about e to the ijk here. If ijk is 1, 2, 3, or 2, 3, 1, or 3, 1, 2, then it's an even number of swaps. The reason is 1, 2, and 3 is the original, and that's a zero number of swaps, which is even, so that just means if 1. If you have a 2, 3, 1, then all we've done is uh, we flipped, we flipped that once, and then we also flipped it twice. So we did 2 flips here. I think here's when you did one single flip. Look at that, you flipped that 1, and so now it becomes negative 1. So this is odd. 1, 2, 3 swaps. These are the swaps, IJK. I didn't mean 1, 2, 3s, whatever. IJK and 1, 2, 3s, these are the indices. They're not like numbers, it's indices. So here you have to swap them an even number of times, it becomes 1, and here you swap it an odd number of times, it becomes 0, or if you repeat them, then it becomes 0. Alright, so that's great. Here's a way to do the cross product quickly. I did it the specifically for the position vector with a gradient here, so to show how that actually equals 0, but I'm also going to show other way to do the cross product, which is even faster. So you could say dx, dy, dz, and then you can just do x, y, and z, and then you're done with the cross product, because all you gotta do, and I guess I will rewrite this a few times, boom, boom, and boom. The only reason I'm writing it 3 times is because I can't use my finger to cover up this stuff. I have to like mark that I'm covering it. Boom. And so when you sort of use your finger and you like cover this up, then you see the determinants popping up. And that is actually the answer. So you'd find a vector. I'll use it in gray because what's really happening is we're taking these little things like dyz and then dz of y. As you can see, dyz and dz of y. That's exactly what we have right here. Like this. And this is like this. So these are cross products that we're doing, and we're just kind of shoving them right underneath. You don't really have to write all this stuff out, but you just need one copy of this. And then you use your finger to cover them up, and you just write the answer. So boom, you're done with the cross product in a single step. I don't like doing too much stuff, so I like having quick shortcuts to solve things. It's nice. All right, and then oh boy, there's so many different weird things that you could do here. So we're continuing with this cross product business. Yeah, we show essentially why this equals 0 if you're taking the nabla across position vector. Notice how here we're taking the nabla of a position vector, taking the gradient of the position vector, and we get 3. I wonder why. Okay, that's a little bit weird. I'm not entirely sure. I'm not entirely sure why this Notice we have a dj, okay, or sorry, dj with an x vector here. And then here we have a dj with an x vector. Okay, I guess these are different indices here, and then these are matching indices. So if we get matching indices, dixi, then we just get we can sum them up. Okay, so you're just taking you're taking a dot product. I'm not exactly sure why this is even in the upper index. It should just be in the lower index. There's no change, no difference, no meaning there for now. Maybe later. But here you go. We've got dixi, so we're doing a dot product with the nabla here. And we just get, you get dxx, dyyy, dzz, add them up, and it becomes 3. And this again, we're just taking a dot product here. There's no real need to put them in the upper portion here. It's just two indices that happen to match. Okay, and then you just get x squared, y squared, z squared. Boom, it's a dot product. These are position vectors though. So it's the same exact thing as saying same thing as this. Boom. It's very nice. It's very neat. Awesome. Now here's a final way that you can start to look at this. So you take xj, xj, this is just a little dot product right here. Notice that these are paired, and this is the one that's not. So this kind of just becomes r squared or something. You take a little di, and you look at it sort of like a 2r, but it's the exact same thing as saying 2xi. I, it's, remember, we're just really doing this here. So, let's show that a little bit better, perhaps. It's okay to say r squared here, but it's even better if we just shove this whole thing in there, like this. And then we can clearly see how we're taking derivatives of this stuff. These are not pluses, though. These are commas. Oh, no, it is. It is a plus. Boom, boom, boom. So if you take a derivative, you're just getting 2x plus 2y plus 2z, which equals 2xi. So there we go. This is just, we have to sort of keep practicing using these index notations. Super hard, super hard. But we've covered all of this stuff, which is great. There's a few more identities which we might want to write down. Here's one like nabla f. That's dif. This becomes a vector because it's what a vector? I think so, because you're just looking at a gradient. So it becomes like the gradient vector of f. Okay, here's some more stuff. So you can take a scaled vector and you can dot it and you get this. We're not really going to talk too much about these things. They're just things that you have to sort of like read and see and copy down and have them somewhere. This is basically a little cheat sheet. This is a crazy one. That a dot b, here's a gradient right there. So you have to make sure to be very careful about where you put this gradient. So you're taking the gradient of b, you're dotting that with a. You're taking the gradient of a, you're dotting it with b. And then over here, you sort of flip everything and get the crosses. So you got dots and crosses. And then here's a great one. So if you're taking the derivative of some constant vector dotted with some other vector, and you're taking the gradient here, then clearly you're taking a gradient in terms of this b. So the only thing that remains is the constant vector out of this. Um, so here that is in action, another version. So here's only specifically the x position, right? So dx instead of di. Here you're choosing all three dimensions. Here you're specifically choosing the x dimension. And because of that, if you take a partial x for kxx, kyy, and kzz, well, what remains but kx? You're taking a partial of x, so you only get this component out of it. You take the di, and you're going to get all three components left. So that's ki. Right. Now let's get into a little bit more stuff. What have we covered so far? Like we literally just did vectors and indexes, and uh, this differential calculus and integral calculus is kind of the next stuff we got to look at. You don't want to know the Gauss's divergence theorem here. We want to know Stokes' theorem. Um, we want to know that fields are written like this, where they're actually three indices all in one. So F1, F2, F3, it's actually a function of X, Y, and Z in all three positions, all three coordinates. That's crazy. Um, Here's a little Jacobian matrix. The Jacobian matrix is a delta J, so a partial J for this field Fi. When we do that, we just have to do partial X, partial Y, partial Z, and then do that for all three components. It's this big matrix. That's the Jacobian matrix. Pretty cool. But we're still kind of doing vector calculus stuff over here, I guess. I don't know, here's the Laplace equation, the Poisson equation, and some more identities to remember. Ultimately, we want to do these integrals. These vector integrals are really important. Here's how we parameterize. The reason is because if you have an integral here, f dot dr, well, think about it. Dr is just basically dr over dt is what? It's r prime. So, we're kind of taking the dr over dt over here, and then we're multiplying both sides by dt, and then put it on this side so that you get dr equals r prime times dt. So this is a good one. And then here's r prime. You're just going to have to figure out what the x, y, and z could be. Because you can do this in 2 dimensions, 3 dimensions, doesn't matter. 2 or 3. This is just a vector work integral. Yeah, take the dot product of your field times this r prime vector. And in order to do that, it's just a whole bunch of steps. First, you got to figure out parameterize t, rt. So here's your xt and yt. And the way to do that is you say 1 minus t times your initial plus t times your final. What does that mean? Let's say it started like at 0, 0 and it ended at like 1, 1. So you could plug those in there and um, you basically just get your xt from 1 minus t times 0 plus t times 1. And you get your yt, 1 minus t times 0 plus t times 1. Once you find your xt's and yt's by parameterizing them, in fact, yeah, once you get your xt's and yt's, then you have to take your derivative. Once you take your derivative, then you dot it with the product with the field, and then you integrate. So there's just like multiple steps you have to take. And I guess I'll maybe write them down here because one is you have to sort of do this little u sub, I guess. Uh, I guess you have to find the dr. Number two is you have to parameterize. Number three, you have to take r prime. Heck, I like to do short annotations, so I will just do like this. R. Then for step three, you have to take r prime. And then for step four, you have to do the dot product. And then step 5, you can do your integral. Put a little close sign like that. So it's good. Boom. 5 steps to do this vector integral. It's like a work integral right here. Change it to dr, or I guess we'll make it dt. Change it to dt, figure out what RT is, take the derivative, dot it with f, and then take an integral. Holy smokes. Next one is the vector flux integral, which is f dot n dr. Again, we have to do this dt situation here. But the problem is nt is like this. I guess it's kind of harder to do, to understand what nt really is. I guess it's like the normal vector. So since this is the normal vector, we do a slightly different type of derivative where we flip it. Similar things, you're just gonna have to find dt, figure out what nt is this time instead of rt. I don't think we have it. An rt. No. So for the second one here, so I'll put it right here. Here using nt, we don't have to find the derivative. It already is a derivative. And then we can dot it. And then we could do the integral. So it's a slightly easier, but this also kind of requires memorizing what nt is. I don't know what to do here. But anyway, we got this final one, which is a 3D vector flux integral. This is for 3D. Notice how this one was for 2D. So you could do a quick little nt here, and this is nice. This is in 2D. It's pretty easy. But if we're going into 3D, now what we have to do is we have to find this area vector. I'm pretty sure that this is supposed to be absolute value. I guess it's not, but whatever. It's not a big deal. So here we have n dot dA is this area times, like this is like the normal vector times the area. So what RU and RV is, here, looking at an area rather than a line. So the area is in terms of some variables. Say UV is either equal to XY or YZ or XZ. It's equal to some pairing of variables because you need an area. So once you find your area vector, 1, 2, and 3, that's nice. Now you're going to take your partials, like say partial X and partial Y, if you're using the XY. Because here you'd have like something here in terms of x and y, something here in terms of x and y, something here in terms of x and y. And so you're taking the partial x, and then you're just going to see what remains out of this. Here you're taking a partial y, and we're seeing what remains out of it. And then once you've done your partial, you have to cross them. So we will try to do this, see how many steps it takes. The first step we have to do is to get du dv out of this. UDV. Once we got DUDV sort of set up, we have to look at RUV. RUV. Once we find the RUV vector, this is a vector here, then we take partials. So it's going to be RU and RV. RU, V, those are just derivatives. Then I say the cross product. Like, you kind of have to find the derivatives before you can do the cross product. I mean, technically you could do it all in one step, but let's just go step by step. So RU cross with RV. After you find them, you cross them. And then once you've crossed them, then you have to dot that. Step 5, F dotted with this area vector. You have to dot it with this. Once you've dotted it, then you can do the integral. Step 6 over here. So this one's quite a complicated integral to do. It takes a lot of steps. But there we go. And ultimately down here, we just have some cylindrical coordinate stuff. We really have to know what the position vector is. It's x hat, y hat, z hat, which is r, and r hat direction. X equals r, so oh my god. This is for spherical right here. Spherical. Remember that for cylindrical, we have like x equals r cosine theta. Y equals r sine theta. And then z just equals z. This is how we understand cylindrical coordinates, which is nice. But if you want to go to spherical coordinates, you kind of start with z. You're just like, let's just say that z is a really important direction. It's kind of like our x direction. So we're going to stick with z. And then, oh my god, I don't know what happened here. Once you got z, then you start looking at x and y as kind of like being another plane. So you got r cosine theta and then r sine theta. And then you can look at it sort of like a subplane, like cosine phi, sine phi. And that's how you get your spherical. Notice that these do not have vectors except for unit vectors. They don't have any like actual vectors. So dr equals this stuff right here. Hopefully. I mean, that might just be cylindrical coordinates on the side. No, that's spherical. That's spherical. So there's like two different things. You gotta make sure that you recognize between the cylindrical version, which has a z in it, or the spherical version, which has this phi hat in it. If you're doing cylindrical, it's nice and easy. You're just doing regular old, it's like the gradient of f. You're doing partials of r, partial of theta, partial of z, and you're dotting it by the f in that r hat direction, or phi hat, or z hat. And then you have to take this middle component and divide it by r. But over here, you also have to divide this phi hat component by 1 over r sine theta. And then similarly with the dot product, we have to do some crazy stuff. 1 over r This is for the spherical version. Oh, sorry, this is cylindrical right here. So 1 over r times the r fr, and 1 over r times partial theta f theta. Here you have to multiply r times this little component. Here we don't do that. Here you just have a little bit simpler. Here you use like r squared, then you have 1 over r sine. There's a sign in there. There's 1 over r sine. There's no sign in there. What's going on here? And somehow we're supposed to like remember all this. It's kind of crazy. And let's look at the cross product. And this will be the last section. Just the cross products here, where we take this. This is the cylindrical one. Nice and easy. This is the sphere. And you see how we just take 1 over r. We got to multiply the r times the f theta component, and then we do our cross in here. At the end, we actually have to multiply or dot our answer by this vector. So like this is kind of a crazy notation to do the cross product, but what we're doing is we're crossing this. This is like all crossed up. So it'll across here, and across here. So you get your vector, and you're going to dot that with this vector. So that way your solution either has this r hat component, this r times theta component, so that cancels this r out. So you get another r in here, I think. And hopefully this is correct. I mean, it's like really complicated to do this. I'm pretty sure that this is the correct way to do this because it gets the right answer. And then over here, we do this. And this one is absolutely correct because I've checked it a bunch of times. Again, you solve the cross product and then dot it with this bizarre vector right here. Just scales your unit vectors by the term that will cancel out with over here. And so that works out pretty well. Here's another really good vector to know, is that when you're looking at this xyz hat vector, it actually equals this whole thing where you kind of look again at the z hat, you're like cosine minus sine, and then you're like sine theta, cosine theta. And then these things remain the same, cosine theta, sine theta, these are phi's, and then you flip them over here, and you get your r hat, your phi, your vector, your theta hat, and your phi hat, and then you can transform these vectors across, and that's amazing. Over here, this is for the thetas, for knowing if you're in the z plane or up there or down in the negative z hat direction. Okay, well, it's getting a little bit vague here, but this is super, super complicated stuff. Unfortunately, we have to sort of learn all this stuff for our exam, and yeah, hopefully that was a lot of fun, learning about all this random stuff. The key is we have to practice, practice, and practice, so. Oh, sorry about that, I didn't notice your message. Hey, Londra Safiri, what's going on? This is live. Right, I don't have chat pulled up. Recording. Unfortunately, the chat window is kind of like off here in some other screen, which is kind of hard to see. But yo, thanks for tuning in. Thanks for watching. And